the human race had figured out the clue, not the clue, the pattern of the solar system. Galileo proved that the heliocentric model was, well, he proved that the geocentric model was incorrect by observing the phases of Venus. For once and for all, put that model to rest. For his trouble, he got put in front of the Inquisition and put under house arrest. But as I alluded to, he still made significant contributions to our understanding of the universe, even though they wouldn't let him look through his telescope anymore. What he did, he actually built these elaborate marble tracks in his villa. I mean, him being under house arrest, don't feel too bad. He had a nice place to live. But he started doing experiments with motion, trying to figure out the motion of bodies on Earth, and trying to figure out gravity. This is where he realized that if it's just gravity, that the objects will accelerate with the same rate. Acceleration is a change in velocity, so they will speed up at the same rate, regardless of what their mass was. And this was pretty astounding, because first it goes against our senses. If we drop a ball and a feather, we know the ball is going to hit the ground first. And many people still to this day, if I ask my students this, they say, oh, it's because the ball is heavier. That's why it hits the ground first. And then those of us who learned about this or remembered it from grade school, actually my classes keep telling me they never heard this story before until now, about Galileo dropping 2 balls from the Leaning Tower of Pisa. I find that hard to believe, but maybe that's our new educational system. But anyway, whether it's actually not even clear that he did this. It's maybe an urban legend. If he did do it, it was as a demonstration. He actually did the experiments with this using marbles going down a track. What he was able to, he was able to take the friction out of that, whether it's friction by rolling or whether it's air resistance. Before Galileo, our favorite scientist before that, Aristotle, had laws of motion. One of them was pretty simple. An object at rest will stay at rest. That one's pretty obvious. Everybody still agrees to that to this day. We say it more scientifically. An object at rest with no net external forces on it will stay at rest. But then he said, if you give it a force, it will start to move. And we still agree on that. But what Aristotle thought was that he said that there was this property called inertia. We still use that word, but he thought inertia was kind of like temperature or heat, and that it would slowly dissipate. So when I kick a ball, it gets a lot of inertia, but then it's going to slow down because that inertia is going to kind of leak out. And he had different laws of the universe for the things on Earth and the sky, right? He thought that the objects went around the sky in circular motion. That was the natural path of something, and that somehow they kept their inertia. They didn't lose their inertia the way objects on Earth did. He knew that objects on Earth tended to go into a straight line, and then they would just slowly slow down. He had no idea about friction or air resistance. We know today that the ball slows down because of the friction between the ball and the ground. If we kick an ice puck on a skating rink, it won't slow down. It'll go until it hits the edge of our rink, because the ice, there's not as much friction on there. So Galileo, with his marbles rolling down these tracks, was able to get the friction out of the equation, and he realized he used different mass balls, and they all went down. They had the same acceleration. This doesn't make a lot of sense. That because even going beyond the heavy part, the reason why it doesn't make a lot of sense is think about trying to push a giant dump truck. Let's say you get stuck in the, you're a moving van, you get stuck in the mud in the moving van, you're trying to push that van out of the mud. It's going to be a lot harder to push than it will be if you had a tiny little Prius, right? A little Volkswagen Beetle is easier to push. We know that it's harder to move massive objects. And you may think that's because of friction, but it's not. It's try and kick a Zamboni, or one of the big machines that they clean the ice with on an ice rink. It's not going to move as fast as the puck that you kick. And so more massive objects are harder to move. And so Galileo went to his deathbed trying to figure this out. If more massive objects are harder to move, then why does the mass of an object not matter when they're falling, right? I mean, you could, instead of a pushing an object, it's pulling. You could do the same thing. It's a lot easier to pull something lighter than it is to pull something that's heavy. So the Earth somehow pulls on objects regardless of how much they weigh. Some kind of, the Earth sucks, you could say. But if you had a vacuum cleaner and you're trying to, suck in a little piece of paper versus, a piece of a paperweight, right? The paper's going to fly towards your vacuum. The paperweight won't move. So he never quite figured this out. It would actually be 500 years later. Sir Isaac Newton was the person to take Aristotle's laws of motion, Galileo's new laws of motion that included friction and air resistance, and come up with a theory on how motion works. And again, I mean a scientific theory, not what he thought, but something that he could make predictions on. Probably the second most famous law of physics, besides E equals mc squared, is F equals ma. Force is equal to mass times acceleration. This is Sir Isaac Newton who came up with that. He actually had to invent calculus in order to really understand motion. By the way, he did this during self-isolation during a plague during the time. So maybe we'll get some new laws of physics out of this coronavirus here. Now that he couldn't do anything, he was stuck in his room, and he came up with how not only a law of how motion and forces worked, but gravity to boot. So he has several laws we're going to learn of. 4 laws we're going to learn of today. So first we have to take a step back and think about how we describe motion. I mean, almost everybody talks that we have an innate feeling about how fast we're going. We call that speed. Scientifically, we use the word velocity to convey some more information. Speed is just how fast you're going. For instance, 55 miles an hour. Velocity would give you a direction as well. 55 miles per hour going east or going north would be a description of velocity. But we also know that speed can increase or it can decrease. The scientific word for that is acceleration, is a change in velocity, and not just a change in speed, as we'll learn, but a change in velocity. And it is it also has a kind of a direction. If you're a math geek, we would call this a vector, but you just need to know that it has a direction to it. You can your velocity can be increasing or it can be decreasing, and kind of the direction goes there. Just to give you an idea of acceleration, it's so up here we're going from 30 miles or kilometers per hour. We step on the gas. In fact, in our car, what do we call that? Many people call that the accelerator. We step on that, and it makes our speed increase. It makes the car accelerate. Let's do the other simple example. We could just as easily call our brake pedal an accelerator, because when we step on the brakes, it changes the speed of our car, changes the velocity of our car. Some people like to call that deceleration, but we just scientifically we just say that's a negative acceleration. But the one that you might not imagine, what if I go around a curve going 60 kilometers per hour? Well, my speed did not change. My speedometer, I look at my speedometer, it's not going to change at all. So you might not think that there's any acceleration there, but there is, because remember, velocity, acceleration is a change in velocity. Velocity is a direction. We are changing our direction as we go around that curve. Even if we do it at a constant rate, our speedometer wouldn't say we were moving, but our eyes would tell us we were changing direction. Or if we had a compass in our car, it would tell us that we were changing our direction. So why do we care about acceleration? Because that is what Newton's laws. That's the A in Newton's laws. It's not the velocity; it's the acceleration that is changing. So Newton's first law of motion is really Aristotle's law of motion. An object at rest will remain at rest unless acted on by an unbalanced force. That's still Aristotle. But then this is where he breaks free. This is where he breaks away from Aristotle. There's no magical inertia that gets evaporated. That ball will go on forever and ever and ever with the same speed. Once the force is gone, that ball would go on forever. Now, we know that soccer balls don't go on forever when we kick them on Earth. That's because there is a force on them. After we kick them, there's a force. There's a force called gravity. There's also air resistance, but the main thing that slows down a ball while it's in the air is gravity. And so it actually slows it down as it's going up, and then it's going to speed it up coming back down. In the horizontal direction, if there's no air resistance, the speed doesn't change in the horizontal, but the vertical part's getting slower and slower, goes to zero, and then goes back down, getting faster and faster until it hits the ground or it hits the net or something like that. So there's Newton's first law of motion. So what do I mean by forces? When we say F equals ma, we have to be careful. That F is really the sum of all the forces on a object. For instance, we have our textbook on a shelf here, or a desk here. Gravity doesn't go away. It doesn't stop falling towards the earth because there's no gravity on that book. There's still the weight or the force of gravity on that book, but we call it the normal force. The desk is pushing on the book, and it's pushing on exactly equal and opposite so that this book is not moving up and down. That force is actually the electromagnetic repulsion between the electrons in the book and the electrons in the surface of this desk. I mean, we talk about things being solid and rigid, and we can stand on them, but it's really the electromagnetic force. The reason why you don't fall through the crust of the earth is because of electricity and magnetism. The electric repulsion, like charges, the electrons have negative charges, they repel each other. And so what we consider a solid is really kind of an energy field. I put it to you, if you looked at the very, very quantum level, even the microscopic level, or the atomic level, this book never really touches the desk. It's kind of floating on this energy field, this electromagnetic energy field. And we'll come back more to that in the next chapters, actually. So Newton's second law is the summation of all the forces is equal to the mass times the acceleration. This is We use this to describe how rockets move. This is we can put some math on why it's harder to move two refrigerators than just one refrigerator. Put them on wheels so you get friction out of it. It's still going to be harder to push two of them because their mass is going to be twice as much. And if I want to move that refrigerator twice as fast, I want to push it with twice as much force. It's a linear relationship. The force is equal to the mass times the acceleration. The change in the speed is going on here. This was his second law of motion. He had a third law of motion that you probably heard of. Probably heard of it in English. For every action, there is an equal and opposite reaction. We use this to talk about sociology and things like that. But it's a law of physics. It's a law of motion. If you're a swimmer, you know this. If you want to get a little extra boost, you kick off on the wall, and you notice you kick in the opposite direction that you want to go. You can do that kick, and the wall, by Newton's third law, is going to give you a kick in the opposite direction of equal and opposite magnitude. It's going to make you go in the opposite direction. If you're not a swimmer, you walk. This is how you walk. You push. If you ever notice how you walk, you push in the opposite direction you want to go, and the earth pushes back on you. And the force is exactly the same. The earth is pushing on you, but you're pushing on the earth. So the question is, if the forces are the same, you're moving, why doesn't the earth move? I mean, the earth moves, but why doesn't it move? Because of you walking, you pushing on it. In that, we go back to Newton's second law. We can rewrite it as acceleration is equal to the force divided by the mass. The mass of the earth is this number. Remember our scientific notation, that's 6 with 24 zeros behind it. I don't even know what that's called. I'm sure there's some word for 10 to the 24th. It's not a million, it's not a billion. I don't know what that is. That's why scientists we don't want to have to remember all Googles and whatever they use. We use scientific notation. That's 6 with 24 zeros behind you. You only weigh one. You have 1 zero behind you. About 70 kilograms is an average person's mass. The force is the same, but the masses are very, very different. Cars are the same thing. Rockets are the same thing. Newton's third law of motion explains almost everything, all of our pieces of technology. The rocket is interesting because back in the day, normal people didn't think rockets would work in space. In fact, some people on YouTube still think rockets won't work on space because they understood Newton's third law, sort of. If you swim, you're pushing on the water and the water's pushing back on you. Well, they said, well, how's a rocket going to swim in space? Because there's no air to push on. That's not that it's doing that. What's happening in a rocket is the gases inside of here. The action is a chemical reaction, pushes all this gas out, this hot gas outside, and the gas pushes back up on the rocket and makes it go up. By the way, if you ever get stranded in space, remember Newton's third law, and that'll get you back wherever you're going as long as you've got something you want to throw. You've got a nice big wrench here, and you want to get back to your spacecraft. Throw it in the opposite direction. And you have to let go. Sorry, it may be your favorite wrench, but you got to let go of it or it's not going to work. You could swim your arms as much as you want. They were right about that. You're not going to go anywhere. You're not going to push on that. But if you can throw away something on your suit, you will go off. Make sure you throw in the opposite direction then. And you want to throw it the opposite way you want to go. So with Newton's laws of motion, he said about there were lots of experimentation on that. Actually, a friend of his, this was about the time that Halley's Comet was coming towards Earth. Comets were big deals back then. They were like they thought they were omens of disasters happening. they kind of went against the cuckoo clock model of the solar system. I remember Kepler, he figured out the code, but he thought it was like some giant musical instrument. Somebody tried to get Newton to explain what about comets, and so he tried to use his laws of motion to understand how a comet would work. And so that led him to think about gravity. Another probable urban legend. I mean, the urban legend is, right, he was sitting under the apple tree and the apple fell on his head and went, "Oh, I understand gravity." But a more believable legend is, it was such a legend that it was painted here. Back in the day, it was painted. He was in his backyard, and he was watching the apples fall from the tree, and the moon was out. The moon is out in the afternoon sometimes when the sun is setting and the moon comes up. You can kind of see the moon during the daytime. He saw the moon. He saw the apples fall, and he had this epiphany that the moon was actually falling towards the earth by the same force that was making the apple fall towards the earth, by gravity. I mean, this was kind of crazy, right? Sounds kind of crazy. Why? The fact that it was falling towards the earth, that's not so crazy. But why doesn't the moon hit the earth the same way that an apple that falls from the tree hits the earth? And he devised a thought experiment on this that I'll describe, and then we'll watch a short video on. Think about how can you overcome gravity? If you especially if you're out playing catch, right? How do you get that ball to go further before it hits the ground, right? If you just drop a ball, it's going to hit the ground very quickly. But if you throw it like a baseball or a football, you can get it to stay in the air longer. You can get it to go further in the horizontal direction, and you can change the angle to get it to do that. But about 45-degree angle is going to give you the longest range and the longest time in the air. But another way that you can make it stay in the air longer and go further is to throw it faster. The faster you throw it, the further it's going to go, and the longer it will stay in the air. Well, imagine if you threw it fast enough, you could actually get it to never hit the ground. And that's what his thought experiment was. They didn't have footballs. He did it with cannonballs. Let's watch this video.
To show how gravity works on Earth and in the skies, Newton designed a thought experiment. He imagined firing a cannon from the top of an extremely tall mountain. From his first law of motion, he knew the cannonball would travel in a straight line at a constant speed forever. But gravity pulls the ball downward. If its speed is low, the cannonball hits the earth near the mountain. The higher the speed, the farther away the ball lands. If you throw it faster, it comes farther away. Even faster, farther away. Even faster, it may go 1,000 miles. Even farther, it may actually go almost halfway around the Earth, and there hit the Earth. You can imagine that if its speed were high enough, the cannonball would travel all the way around the Earth and settle into orbit.
The orbit of the cannonball around the Earth was a balancing act between the cannonball's tendency to fly off in a straight line and its being yanked back towards the center of the Earth continuously by the force of gravity. So in Newton's picture of the world, there were two things. The natural tendency of an object to travel in a straight line, which was true on Earth or in space or anywhere, and there was the attraction of gravity, which was true on the surface of the Earth, and it was true up in space.
Newton's breakthrough was to see that the moon's orbit around the Earth and a cannonball's motion on Earth were governed by the same law of gravity.
Okay, so that was actually an incredible insight, and believe it or not, it allowed him to experiment with gravity easier than it is on Earth. By using his two laws of motion, F equals ma, he could, that law of motion, he actually figured out that gravity has to be proportional to the mass of the object. In order for them to fall at the same rate, that means the gravitational force on heavier objects has to be stronger than it is on light objects. But that would just give him part of this equation. That would tell him that it's proportional to the mass. And otherwise, it was incredibly difficult. Imagine trying to drop a ball and time it with no, they didn't have stopwatches there. Trying to figure out, do experiments on gravity on Earth is actually still harder than it is to do in outer space. So that epiphany that gravity was the same, that the moon really was falling towards the Earth by the same force that the apple was falling towards the Earth. And the reason why the moon does not hit the Earth is because it's moving fast enough in the perpendicular direction. Now he's got all of this data, right? All of the hundreds of years, starting with the more precise one, starting with Kepler, hundreds of years of data on how the moon orbits the Earth and how the planets orbit the sun. He actually was able to use Kepler's laws to find a universal law of gravity that he would never have been able to find on Earth. This distance squared term, no way he could do this. In fact, there are theories of gravity that say that there's some other terms here when you get things that are very close that we just can't measure yet, because believe it or not, the force of gravity is the weakest of all the forces of nature. Even though it's the one that's most apparent to us, it is actually the weakest of all the forces of nature. This is a universal gravitational constant. This kind of tells us the force of gravity. And it's the same everywhere in the universe. It's the same between the Earth and the moon. It's the same with the apple and the Earth. It's the same between the Earth and the sun. And any two objects have a mutual force of attraction on them by gravity. And it's quite weak. But we see it because our objects are incredibly massive. The Earth, as I saw, is incredibly massive. The sun is even more massive. So this is his formula: universal law of gravity times the mass of one object, the mass of the other object divided by the distance between those objects squared. And so this is his universal law of gravity. He has three laws of motion and another law of gravity, and between that you can figure out almost any motion in the universe, almost. But this does explain, here is his law of gravity: F is equal to GME/mB. Let's talk about Galileo's balls. Sorry about that. Divided by the radius of the Earth square is equal to, this is his second law, force is equal to the mass of the ball times its acceleration. Well, notice I have the mass of the ball on this side, the mass of the ball on this side. This is mass of the Earth and the radius of the Earth square. The mass of the object falls out. So just for gravity, a feather, a bowling ball, a dump truck, all will fall with the same rate. The difference in why they fall has to do with the air resistance. And it's not that the air resistance on the feather is stronger. The air resistance on the bowling ball is much stronger, but it's the relative strengths of those. There's not a lot of force of gravity on the feather because it doesn't have a lot of mass, so the air resistance can compete with it a lot more than, there's even more air resistance on the bowling ball, but it's tiny compared to the force of gravity. So a way to really understand the force of gravity is the force of gravity does depend on the mass, but because more massive objects are harder to move, they fall out, and the acceleration due to gravity is the same, not the force of gravity. The The force of gravity on the bowling ball is much stronger than it is on the feather. But the accelerations are the same. Okay. We don't have time to go through all this. You want to go through these? I mean, this is just kind of you've already done this on our gravity and motion lab. But if you'd like to see it, again, you can go through these slides. Your weight is what changes. Your mass never changes. I mean, your mass changes depending on your diet and your isolation. My mass is going up a little, kind of crazy, but my mass isn't going to change if I'm on Mars, but my weight will, because the weight depends on the mass of the planet you're on and its radius. So you can kind of see your weight on different objects. The moon, for instance. Check this out.
Well, in my left hand, I have a feather. In my right hand, a hammer. But I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
So they did.
Mr. Galvin.
Also notice, compare that to the bowling ball and the feather in the vacuum on Earth. That hammer fell a lot slower than the bowling ball would be on Earth. So kind of demonstrating both here. There's no air resistance. That's why they fall at the same. They fall slower because the gravity is less on here. You also watch these. Watch them skip around. Right? They're happy. I'm sure they're happy being on the moon, but they're not very heavy on the moon. Their weight is much different on there. Your weight can also change depending on whether you're accelerating or not. The classic example of this is in an elevator. If you live in a high-rise, wait till it's late at night and take your bathroom scale out and hit the top floor, and you'll notice that your weight changes a little bit as the elevator is accelerating. Usually right just when it starts. Or when it starts going down, your weight will change. Your weight will be a little heavier as you're accelerating up. Your weight will be a little bit lighter as you're accelerating down. And if, heaven forbid, that rope breaks in the elevator, you will experience, for a couple of seconds, free fall. You'll be weightless. And then you'll die, but, well, maybe you won't die, but you'll be hurt because the urban legend is if you jump up, you're going to save yourself, but that's not going to work. You're still going to crash down into this ground at about 60 miles an hour. So not going to be nice. Let's watch. I want to show you something else. You may have seen pictures of the astronauts on the ISS that are weightless. Many people think it's because there's no gravity up there. But of course, there's gravity up there. The ISS would just keep on going in orbit. I mean, it wouldn't be in orbit. It would just go straight in a path. It's weightless on the ISS because let's go back to my because they're in free fall. On the ISS, I mean, the ISS is this giant space platform. The ISS is really just kind of a protection. It protects them from radiation. It protects them from, gives them a place to breathe. They are actually they're in orbit just as much as it is. It's just kind of enclosure around there. What we feel as our weight is really the Earth pushing on us, keeping us from falling in towards the center of the Earth. There's nothing keeping it falling other than the astronaut's speed. Now, it takes a tremendous amount of energy to get an astronaut into this orbit and this machine into this orbit, but really it's not. They'd be going around just as much without that, and so that's why They feel like they're weightless. And apparently, I mean, you felt this on a roller coaster, maybe, or if you've been driving your car too fast and you hit a bump and you get a little air, you'll feel that weightlessness when nothing is pushing on you and you're moving. It doesn't feel that great. You get the little butterflies in your stomach, but apparently on the ISS that goes away pretty soon. Okay, we're going to skip ahead. But now with Newton, we finally understand. We understand gravity. We understand the solar system. It's not some giant cuckoo clock. These objects are orbiting around the sun by the force of gravity. Gravity is like a rubber band that's pulling them around. They pull on the sun as well, but the sun is much more massive. So the sun in this system stays stationary. We're going to learn the sun is not stationary. It's going around another more massive object. But in order to understand the solar system, we don't need to know about that yet. The planets are orbiting around the sun because of the force of gravity. The moon is orbiting around the Earth because of the force of gravity. And it's exactly the same force that makes an apple fall from the tree down to the surface of the Earth. And so he understands the laws of physics, the law of the universe, we understand how the solar system works now. And later on, the solar system got bigger. Herschel built this giant telescope. We'll learn about this next week. It's like a giant bucket for light. You cannot see Uranus and Neptune with your naked eye. You can see all of the other planets. I encourage you to go out tonight or in the evening now, and you'll see the brightest star in the sky is actually going to be Venus. If you, for those of you who like to get up early in the morning, you can see Mars and Jupiter and Saturn in the early morning sky. They look like stars, but you can download an app on your phone, Skyview, for instance. It'll tell you where to look for these planets. Venus is spectacular now; it's so bright. So they found this planet with a telescope. They were keen to predict, right? Of course, all of Kepler's laws, remember, they work to this day. So Newton's law explains Kepler's law. Every object, the comets, all these objects, they fit well within Newton's law of motion and gravity until we discovered Uranus. We discovered Uranus and everybody was keen. Newton was gone by this time, but everybody was, as scientists, we want to test our theories. We want to make sure Newton's law of gravity really works. And so we tried it on this new planet, and guess what? It did not work. It sort of worked, but it wasn't precise. It did not match the predictions. And science struggled with this for more than 50 years to figure out what this was. What was going on here? It actually, they were saying, well, maybe Newton's wrong. Maybe gravity works differently at long distance or something. This thing was much further away. Maybe it doesn't work out there. Maybe there's another term, instead of always being 1 over r squared, maybe there's a different term in there. We'll come back to that. There's some people, not just YouTubers, there's some people who, some real scientists who think that could be the case, not on the scales of the solar system, but on the scales of the universe. Maybe gravity works differently out there. We don't have any evidence for that yet, unless that is one explanation for dark energy, or maybe dark matter, is that we don't quite understand gravity. But we'll come to that in the upcoming weeks. Leverrier, a French mathematician, figured this out. He was a theoretical astronomer as well. He made a hypothesis that, well, we just discovered another planet. Maybe there's another planet out there. Gravity is a mutual force. And these things are very far away from the sun. The reason why they are in orbit is because of the sun. But if I have two really massive objects, they pull on each other. So Leverrier made a hypothesis that there was another planet out there that was pulling on Uranus. And that's why its orbit didn't quite match. And he he actually was able to predict the mass of this planet and where it would be. And soon after he published his predictions, Gottfried Galle went out and actually discovered almost, very close to where Leverrier said it would be. They actually share the discovery of this planet. That Leverrier actually predicted that a planet existed, and we went out and found one. Pretty cool. We're actually, we think this might be happening right now. We'll learn about this in I think it's not next week, but week after that. But we think there's another massive object further out in our solar system. Some people call it Planet X. Some people call it Planet 9 because we demoted Pluto's not a planet anymore. This would be a giant planet, much bigger than Pluto. Might be as big as Neptune, actually. Because not the orbits of the planets, but some of the orbits of the comets out there in the Kuiper Belt don't quite match what we would expect them to. So we think there's something very massive out there that's pulling on them. One of the hypotheses is it's another planet. Another hypothesis is that it's a primordial black hole that's out there. But don't worry, neither one of those objects, regardless of what you'll read on Facebook or whatever your favorite popular social media is, that's sort of sciencey or pseudosciency, right? Very often you'll hear about the Nemesis planet that's about to, smash into Earth, and they'll talk about this planet X being that, or this black hole is going to gobble up the entire solar system. That black hole is about the size of a tennis ball, and we're going to learn they're no more dangerous than a star or anything out there. So neither one of those really has going to, it barely affects the motion of a couple of comets out there. It's not going to hurt the Earth at all. But this was a triumph of science, right? First of all, we questioned Newton's laws. We didn't just say, "Oh, Newton figured this out. We're not gonna make any more observations." As soon as we discovered something, we tried to use Newton's law. It didn't work, and we struggled to find the problem, and we discovered a new planet in the process. That's the way science works. We don't, people say Newton's book was called Principia. It is renowned by scientists as the greatest book ever written. But even that, we do not, we question it, and you're going to see we're going to continue to question things in there. The next question on that was also by Leverrier. He noticed so he's like, well, I just discovered a new planet. Let's look for some more. So he started to even more carefully study the orbits of all the planets to see if any of the other planets did not quite match up with what Newton would predict. And he found one. He found Mercury. Mercury has an even stranger orbit. It's not like it's getting tugged on a little bit. Newton's orbit is what we say is precessing. It never comes back to the same place. Next year, like the Earth a year from now, will be basically the same place we are now, relative to the sun. Okay, we'll be in a different part of the galaxy. Not really. The galaxy is really big. We don't move that much in a year. But we basically come back to the same place every year. Mercury does not. And Mercury years are much shorter than Earth years. They're like a month, and so this is an easy thing to actually observe. It doesn't come back to the same place. Leverrier is like, well, there must be another planet here. He hypothesized that there was another planet that was closer to the sun than Mercury. It was just very difficult for us to see because it was so close to the sun, and the light from the sun would always wash it out. It's actually very hard to see Mercury for that same reason. You have to see Mercury, you have to wait right till the sun goes down or right as it's coming up. It's the only time you can really see Mercury with your naked eyes anyway. So he hypothesized, for you sci-fi fans, he named that planet Vulcan long before Star Trek. He named it Vulcan, but it's not there. We've never found a planet there. We actually have we have 2 solar probes now that are orbiting within the orbit of Mercury. There's not a planet there. So what's going on with the precession of Mercury? Are Newton's laws wrong? It would actually take another 50 years for us to actually understand the precession of Mercury. And that was with Einstein's theory of relativity that he developed. This was a revolutionary concept in physics that completely departs from the classical description. So he went against the two great scientists that came before him, Galileo and Sir Isaac Newton. Remember, Galileo really discovered relativity, right? When an object in motion keeps that motion. It's the reason why the birds don't fly backwards when they get off the earth. It's because they're already moving 1,000 miles an hour. When they do that, all motion is relative, Galileo discovered. Einstein kind of perfected that notion. In order to do that, he had to come up with the concept that space and time are real things, and that there's a space-time continuum. The fabric of the universe is this the space-time continuum. There's not, and that's how he described gravity.